A bombsight is a device used by aircraft to accurately drop bombs. Bombsights are a feature of most aircraft from World War I on, first found on the purpose-designed bomber aircraft, and then moving to fighter bombers and modern tactical aircraft as these aircraft took up the brunt of the bombing role. A bombsight has to estimate the path the bomb will take after release from the aircraft. The two primary forces during its fall are gravity and air drag, which make the path of the bomb through the air roughly parabolic. There are additional factors such as changes in air density and wind that may be considered, but these are only a concern for bombs that spend a significant portion of a minute falling through the air. These effects can be minimized by reducing the fall time through low-level bombing or by increasing the speed of the bombs. These effects are combined in the dive bomber. However, low-level bombing also increases the danger to the bomber from ground-based defenses, and accurate bombing from higher altitudes has always been desired. This has led to a series of increasingly sophisticated bombsight designs dedicated to high-altitude level bombing. Since their first application prior to World War I, bombsights have gone through several major revisions. The earliest systems were iron sights that were preset to an estimated fall angle. In some cases these consisted of nothing more than a series of nails hammered into a convenient spar, lines drawn on the aircraft, or visual alignments of certain parts of the structure. These were replaced by the earliest custom-designed systems, normally iron sights that could be set based on the aircraft's airspeed and altitude. These early systems were replaced by the vector bomb sights, which added the ability to measure and adjust for winds. Vector bombsights were useful for altitudes up to about 3,000 meters and speeds up to about 300 kilometers per hour. Starting in the 1930s, mechanical computers with the performance needed to solve the equations of motion were incorporated into the new tachometric bomb sights, the most famous being the Norden. Later in World War II, tachometric bomb sights were often combined with radar systems to allow accurate bombing through clouds or at night. When post-war, studies demonstrated that bomb accuracy was roughly equal when optically or radar-guided. Optical bombsights were generally removed and the role passed to dedicated radar bombsights. Finally, especially from the 1960s on, fully computerized bombsights were introduced, which combined the bombing with long-range navigation and mapping. Modern aircraft do not have a bombsight per se, instead using highly computerized systems that combine bombing, gunnery, missile fire and navigation into a single head-up display. These systems have the performance to calculate the bomb trajectory in real time as the aircraft maneuvers, and add the ability to adjust for weather, relative altitude, relative speeds for moving targets, and climb or dive angle. This makes them useful both for level bombing, as in earlier generations, and tactical missions formerly bombed by eye. Bombsight concepts. Forces on a bomb. It is a basic outcome of Newtonian mechanics that vertical and horizontal motion of a bomb can be considered separately. This makes understanding the motion of a bomb through the air much simpler. There are some effects that operate along the changing path of the bomb, but they are relatively minor and can be considered separately for a basic study. To start with, consider only the vertical motion of a bomb. In this direction the bomb will be subject to two primary forces, gravity and drag, the first constant, and the second varying with the square of velocity. For an aircraft flying straight and level, the initial vertical velocity of the bomb will be zero, which means it will also have zero vertical drag. Gravity will accelerate the bomb downwards, and as its velocity increases, so too does the drag force. At some point the force of drag will become equal to the force of gravity, and the bomb will reach terminal velocity. As the air drag will also vary with air density, and thus altitude, the terminal velocity will vary as the bomb falls. Generally the bomb will slow as it reaches lower altitudes where the air is denser, but the relationship is complex. Now consider the horizontal motion. At the instant it leaves the shackles, the bomb carries the forward speed of the aircraft with it. This motion is countered solely by drag, which starts to slow the forward motion. As the forward motion slows, the drag force drops and this deceleration diminishes. The forward speed is never reduced entirely to zero. If the bomb was not subject to drag, its path would be purely ballistic and it would impact at an easily calculable point, the vacuum range. In practice, drag means that the impact point is short of the vacuum range, and this real-world distance between dropping and impact is known simply as the range. The difference between the vacuum range and actual range is known as the trail, because the bomb appears to trail behind the aircraft as it falls. The trail and range differ for different bombs due to their individual aerodynamics, and typically have to be measured on a bombing range. The main problem in completely separating the motion into vertical and horizontal components is the terminal velocity. Bombs are designed to fly with the nose pointed forward into the relative wind, normally through the use of fins at the back of the bomb. It is primarily the wind acting on the nose that causes drag, so the velocity that defines the drag is a factor of the angle of attack of the bomb at any given instant. If the bomb is released at low speeds, it will quickly turn vertical and the velocity will be defined largely by how long the bomb has been falling. However, if it is released at high speed, it may already be close to terminal velocity and can only accelerate vertically after bleeding off some of its horizontal speed. Reaching terminal velocity tends to flatten the trajectory, keeping the bomb in the air longer, and thereby allowing the horizontal speed to act over a longer time, extending the range. Finally, consider the effects of wind. Wind acts on the bomb through drag, and is thus a function of the wind speed. This is typically only a fraction of the speed of the bomber or the terminal velocity, so it only becomes a factor at very high altitudes where this small force has enough time to build up to a measurable value over time as the bomb falls. However, the bomber itself is also affected by the wind. The bomb will leave the aircraft with both the forward airspeed of the bomber, as well as any additional motion due to the wind. This velocity is added to the velocity of the aircraft, and may represent a fairly significant adjustment. The difference between the impact point and where it would have fallen if there had been no wind is known as drift, or cross-trail. The bombsight problem. In ballistics terms, it is traditional to talk of the calculation of aiming of ordnance as the solution. The bombsight problem is the calculation of the location in space where the bombs should be dropped in order to hit the target when all of the effects noted above are taken into account. In the absence of wind, the bombsight problem is fairly simple. The impact point is a function of three factors: the aircraft's altitude, its forward speed, and the terminal velocity of the bomb. In many early bombsights, the first two inputs were adjusted by separately setting the front and back sights of an iron sight, one for the altitude and the other for the speed. Terminal velocity, which extends the fall time, can be accounted for by raising the effective altitude by an amount that is based on the bomb's measured ballistics. When windage is accounted for, the calculations become more complex, as the wind can operate in any direction. Bombsights generally recalculate the windage by converting it into the portions that act along the flight path and across it. In practice, it was generally simpler to have the aircraft fly in such a way to zero out any sideways motion before the drop, and thereby eliminate this factor. This is normally accomplished using a common flying techniques known as crabbing or side slip. Bombsights are sighting devices that are pointed in a particular direction, or aimed, although the solution outlined above returns a point in space. Simple trigonometry can be used to convert this point into an angle relative to the ground. The bombsight is then set to indicate that angle. The bombs are dropped where the target passes through the sights. The distance between the aircraft and target at that moment is the range, so this angle is often referred to as the range angle. Although dropping angle, aiming angle, bombing angle, and similar terms are often used as well. In practice, some or all of these calculations are carried out using angles and not points in space, skipping the final conversion. Accuracy. The accuracy of the drop is affected both by inherent problems like the randomness of the atmosphere or bomb manufacture, as well as more practical problems like how close to flat and level the aircraft is flying or the accuracy of its instruments. These inaccuracies compound over time, so increasing the altitude of the bomb run, thereby increasing the fall time, has a significant impact on the final accuracy of the drop. It is useful to consider a single example of a bomb being dropped on a typical mission. In this case we will consider the M65 500-pound general-purpose bomb, widely used by the USAAF and RAF during World War II, with direct counterparts in the armories of most forces involved. Ballistic data on this bomb can be found in Terminal Ballistic Data, Volume 1. Bombing against men standing in the open. The 500 pounds has a lethal radius of about 107 meters, but much less than that against buildings, perhaps 27 meters. The M65 will be dropped from a Boeing B-17 flying at 322 km per hour at an altitude of 6,096 meters in a 42 km per hour wind. Given these conditions, the M65 would travel approximately 1,981 meters forward before impact, for a trail of about 305 meters from the vacuum range, and impact with a velocity of 351 meters per second at an angle of about 77 degrees from horizontal. A 42 km per hour wind would be expected to move the bomb about 91 meters during that time. The time to fall is about 37 seconds. Assuming errors of 5% in every major measurement, one can estimate those effects on accuracy based on the methodology and tables in the guide. A 5% error in altitude at 20,000 feet would be 1,000 feet, so the aircraft might be anywhere from 19 to 21,000 feet. According to the table, this would result in an error around 10 to 15 feet. A 5% error in airspeed, 10 miles per hour, would cause an error of about 15 to 20 feet. In terms of drop timing, errors on the order of 1/10 of a second are reasonable. In this case the error is simply the ground speed of the aircraft over this time, or about 30 feet. All of these are well within the lethal radius of the bomb. The wind affects the accuracy of the bomb in two ways, pushing directly on the bomb while it falls, as well as changing the ground speed of the aircraft before the drop. In the case of the direct effects on the bomb, a measurement that has a 5% error, 1.25 miles per hour, that would cause a 5% error in the drift, which would be 17.5 feet. However, that 1.25 miles per hour error, or 1.8 fps, would also be added to the aircraft's velocity. Over the time of the fall, 37 seconds, that would result in an error of 68 feet, which is at the outside limit of the bomb's performance. The measurement of the wind speed is a more serious concern. Early navigation systems generally measured it using a dead reckoning procedure that compares measured movement over the ground with the calculated movement using the aircraft instruments. The Federal Aviation Administration's FAR Part 63 suggests 5 to 10% accuracy of these calculations. The U.S. Air Force's AFM 51 to 40 gives 10%. And the U.S. Navy's HO 216 at a fixed 20 miles or greater. Compounding this inaccuracy is that it is made using the instrument's airspeed indication, and as the airspeed in this example is about 10 times that of the wind speed, its 5% error can lead to great inaccuracies in wind speed calculations. Eliminating this error through the direct measurement of ground speed was a major advance in the tachymetric bombsights of the 1930s and 40s. Finally, consider errors of the same 5% in the equipment itself, that is, an error of 5% in the setting of the range angle, or a similar 5% error in the leveling of the aircraft or bomb site. For simplicity, consider that 5% to be a 5-degree angle. In tests, accuracies of 3 to 4 degrees were considered standard, and angles as high as 15 degrees were not uncommon. Given the seriousness of the problem, systems for automatic leveling of bomb sites was a major area of study before World War II, especially in the US. Early systems. All of the calculations needed to predict the path of a bomb can be carried out by hand, with the aid of calculated tables of the bomb ballistics. However, the time to carry out these calculations is not trivial. Using visual sighting, the range at which the target is first sighted remains fixed, based on eyesight. As aircraft speeds increase, there is less time available after the initial spotting to carry out the calculations and correct the aircraft's flight path to bring it over the proper drop point. During the early stages of bomb site development, the problem was addressed by reducing the allowable engagement envelope, thereby reducing the need to calculate marginal effects. For instance, when dropped from very low altitudes, the effects of drag and wind during the fall will be so small that they can be ignored. In this case, only the forward speed and altitude have any measurable effect. One of the earliest recorded examples of such a bomb site was built in 1911 by Lieutenant Riley E. Scott, of the U.S. Army Coast Artillery Corps. This was a simple device with inputs for airspeed and altitude which was handheld while lying prone on the wing of the aircraft. After considerable testing, he was able to build a table of settings to use with these inputs. In testing at College Park, Maryland, Scott was able to place two 18-pound bombs within 10 feet of a 4x5-foot target from a height of 400 feet. In January 1912, Scott won $5,000 for first place in the Michelin bombing competition at Villacoublay Aerodrome in France, scoring 12 hits on a 125 by 375-foot target with 15 bombs dropped from 800 meters. In spite of early examples like Scott's prior to the war, during the opening stages of the First World War, bombing was almost always carried out by eye, dropping the small bombs by hand when the conditions looked right. As the use and roles for aircraft increased during the war, the need for better accuracy became pressing. At first this was accomplished by sighting off parts of the aircraft, such as struts and engine cylinders, or drawing lines on the side of the aircraft after test drops on a bombing range. These were useful for low altitudes and stationary targets, but as the nature of the air war expanded, the needs quickly outgrew these solutions as well. One of the earliest fully developed bomb sights to see combat was the German Gotz bomb sight, developed for the Gotha heavy bombers. The Gotz used a telescope with a rotating prism at the bottom which was preset to an angle read from a table of speed and altitude. The bombardier would rotate the prism to keep the target in view, while using a spirit level to keep the instrument level with the ground. Similar bomb sights were developed in France and England, notably the Michelin and Central Flying School No. 7 bomb site. All of these shared the problem that they had no way to account for windage across the aircraft's path, and required the aircraft to fly directly along the wind line in order to be accurate. Even then, the adjustment for drift in setting the trail was normally estimated using a stopwatch and manually timing the flight of the aircraft over the ground, a time-consuming and error-prone process. The first successful attack on the windage problem was made by Harry Wimperis, better known for his later role in the development of radar in England. In 1916 he introduced the drift sight, which added a simple system for directly measuring the wind speed. The bomb aimer would first dial in the altitude and airspeed of the aircraft. Doing so rotated a metal bar on the right side of the bomb sight. Prior to the bomb run, the bomber would fly at right angles to the bomb line, and the bomb aimer would look past the rod to watch the motion of objects on the ground. He would then adjust the wind speed setting until the motion was directly along the rod. This action measured the wind speed, and moved the sights to the proper angle to account for it, eliminating the need for separate calculations. A later modification was added to calculate the difference between true and indicated airspeed, which grows with altitude. This version was the drift sight Mk1A, introduced on the Handley Page 0400 heavy bomber. Variations on the design were common, like the USS Doppy bombsight. All of these bombsights shared the problem that they were unable to deal with wind in any direction other than along the path of travel. That made them effectively useless against moving targets, like submarines and ships, unless the target just happened to be traveling directly in line with the wind. Their motion would carry the bomber away from the wind line as they approached. Additionally, as anti-aircraft artillery grew more effective, they would often pre-sight their guns along the wind line of the targets they were protecting, knowing that attacks would come from those directions. A solution for attacking crosswind was sorely needed.